everybody. Welcome to this week 3 study session. Alright, great. Looks like Al Curtis is here. So again, just please post a message when you first join in so I can tell who's here. And then we will get started. So I saw that Al was in here. For those of you who didn't attend the Sunday session, which should be most of you besides Stephen, basically these study sessions are pretty much here to answer the questions that you have, so I don't come in with that much of a pre-planned agenda or schedule for it. It's basically just looking at the questions you guys have on the homework. Probably, I think, generally I like to focus on the homework. But, so we'll look at homework questions for the week 3 homework. We can, once we're done with that, or if we run out of questions on that, we can cover individual topics or previous quizzes or basically whatever questions come up. But I think starting with homework is generally what a lot of people want to do first. So we might just give it a couple more minutes to just let people join up. And then if you have a question, please go ahead and post it and we will cover them as they come in. All right, hello, Chris. It's good. A couple more people are coming, so we'll give it a couple more minutes, and then we'll just start, and then anybody joining in can pick up as we go along. And then just to be clear, this session's scheduled from 7 till 8. That's somewhat flexible, so if we do have a couple more questions at the end, I can definitely stay a little bit longer and make sure it's all addressed, but that's generally the schedule, and then we'll have another hour on Sunday. But the Sunday one's in the morning, 10 to 11, I think that time is. So that one wasn't quite as popular, but I wanted to have 2 done, and I figured one on the weekend would be good to have just in the morning for any last-minute questions. All right, we've probably waited long enough for a couple people to show up. I'm sure we'll get a few more here and there, but we can go ahead and start. So again, just to reiterate for Chris, who showed up after I gave my little talk, I don't really have a plan for these study sessions. I don't have a set of questions or topics I'm going to cover. It's mostly for you guys to get the questions that you have answered. So if you have a question on, well, I think we'll start with the homework, just because I think a lot of people want to get the homework. It's a priority for them. So if you have any questions on the homework that you've seen, please post it and we'll address them as they come. And then by the end of it, if we've answered all the homework questions, we can start looking at other stuff like previous quizzes or things like that. So Al's going to start us off. He's having a little bit of trouble with problem 3.1 for the homework. So that's problem 3.1, is that right? Let's take a look. Okay, yeah. So let me pull up 3.1 from the start. This is definitely a popular one that it's tricky because you kind of have to have, a lot of people have a tricky time figuring out the actual delay. Okay, so for 3.1, basically the important thing to keep in mind is that you have to understand the differences between circuit switching and packet switch, or circuit switching, packet switching, and virtual packet switching. And so, let me see. Let me just make sure I'm doing the right part here. Okay, so basically they've given you the variables that you need for the equation. So they've told you up front, and it's unfortunate how this is split over 2 pages for my book, but they give you the variables up front, which is, and I'll write out the variables here. So we can get rid of this. So these are the, and this is problem 3.1. Okay. And so the initial variables they give us are n, which is number of hops, which is important because that's the number of hops that, or number of stops each the data has to travel over. L is our message length. B is data rate, and that's bits per second. P is our packet size, and that'll come into play when we start talking about datagram packet switching. H is the header bits per packet, which again is relevant for packet switching. S is call setup time. T is call teardown. And D is propagation delay per hop. So that's the set of variables that we're working with for this problem. Now, we're basically asked to do 3 things for this problem, and you can tell that by just looking at the next page, which is saying it needs to compute the end-to-end delay for circuit switching, virtual circuit packet switching, and datagram packet switching. And then there's some additional information, assuming there's no acknowledgements, signal processing delay at the nodes, assume no header for circuit switching. Okay, that's just a little bit more clarification on which numbers we have to use for which problems. So the way I do it is, despite the order they tell us to do it is in circuit switching, virtual circuit packet switching, and datagram packet switching. But based on the reading, you can kind of see that virtual circuit packet switching is a combination of the previous 2, because it's basically taking a little bit of datagram and a little bit of circuit switching to work together. And so the easier way to do it, I think, is to start with circuit switching, then do datagram packet switching, and finally do virtual circuit packet switching. So we'll start with calculating delay for circuit switching, which is what they tell us to do, so no problem there. Now, based on the chapter and the brief description of circuit switching, there's generally 3 parts of circuit switching. Does anybody have a guess on what those 3 parts are? What makes circuit switching unique compared to packet switching? There's something that circuit switching uses or does that packet switching doesn't have to do. And you might be able to tell by taking a peek at some of the variables we just wrote down here. So Al Curtis says linear setup. I think, yeah, I'm not 100% sure what you mean by linear, but setup definitely. Setup and teardown is something that circuit switching has to do that datagram packet switching doesn't. And so I think I got what you're saying, Al. I think you have the right idea. So with circuit switching, Predefined. Okay, yeah, that makes more sense. So circuit switching, the difference with circuit switching is that you have a predefined predefined path. And so before the call, or before you even start moving the data bits, you've already arranged the route that they're going to take. And that's what makes circuit switching different. And so when we're looking at the time it takes to do a circuit switch communication, we basically have three elements. We have the time it takes to set up the path that we're going to take. Then we have the time that it takes to actually transmit the message. So we'll say M for this one, message time. And then we have the time to tear down. So once we're done with this predefined circuit, we then have to clear that circuit so other people could use it if they need to, or we could set up a different communication on it. So those are the three main things that a circuit switching communication can be broken up into. You have the initial setup of the circuit, then you have the time that we use the circuit to transmit the data, and then you have the teardown time when we're done with the circuit, we need to clear it so that people can use it again. And so looking at these three numbers, we have two of them. Two of these variables are already filled out for us based on the variables that we were given for the problem. So if we look in the book, we've been given setup time, S equals 0.2 seconds. So circuit equals 0.2. And again, that's given. That's one of the variables that are given. Message time, we don't know. But then the teardown time is given as 0.02 seconds. So that's two of the three variables that we have already given to us. But now we need to figure out the middle bit. We need to figure out how much time it takes to transmit the message. And so for this part, basically we're transmitting the message, but then we also have to consider that there's going to be a propagation delay, because we're given D is propagation delay per hop. And we know there's 4 hops. So similarly to how we broke the 3 parts out of the circuit switch time, what do you think are the two? There's basically 2 components of the message transmission time. So I'll break this out here. So there's basically 2 elements of the amount of time it takes to transmit a message. One of them we know is the propagation delay. But then, so let me just give that one since that one's there. Message. So propagation delay, we know there's a delay given per hop. And we know there's 4 hops. So the first part of the transmitting the message time is N times D. Because whenever the data hits a new one of the hop, it gets delayed by a certain amount of time. And that's just how it's given for us. In reality, you might have different propagation times based on hardware or whatever network conditions. But for this case, we know that every hop introduces D delay. But then what's the other part of the time that we have to wait for? Because there's something else here that we have to wait. And how long, what's this extra piece of information here that we need to wait? If we're sending the message, we know that it's delayed per hop, but then what's the other thing that tells us how long it's going to take? And again, looking at the variables on the left here will give you a hint of what we're talking about. So we've accounted for the delay per hop. But what's the actual main thing we're concerned about and how long it takes to transmit the message? Al says message size, and that's true. Ryan says length, so yeah, you're both on the same page. So we know how long the message is, we know how much data is in the message, and looking at B equals data rate, we know what our bit rate is, or we know how fast we can send data. And so we know the length of the message, we know the rate that we can send data at. So how do we figure out how much time it takes to send a message of X length? What's I guess the math that we have to do? We know the speed and we know the amount of data we have. So how do we figure out the time given speed and length? Al gives length divided by b, which is absolutely correct. So we take the length of the message and we divide it by the data rate, or the speed that we can send the message. And that's basic. That's the core thing we're concerned about, because we know how much data we have to send. We know how fast we can send it. That's going to take time. But then we have to remember that we're adding in a delay for each of the hops we hit. So as the data is moving over the wire, when it hits a hop, or when it hits a router or whatever, when it hits a point, a hop, it adds a delay just because of the system. So for our message time, we have propagation delay, which is number of hops times delay per hop to find our total propagation delay, plus the time it actually takes to send the message in the first place, which we know because we know the length of the message and we know the data rate in bits per second. And so this lets us put it all into one big formula where we have C equals 0.2 plus N times D. And I'll put these in parentheses just so we can tell it's a separate part, plus L divided by B plus 0.02. And that will tell us the time it takes, the total amount of time it takes for this circuit switched message to be sent. And let me just make sure that's readable when I pull up the chat. And so now we know all these numbers based on the numbers given to us in the book, so we can just plug into this formula and that'll tell us the amount of time it takes for a circuit switched transmission. And so if you guys want to plug in the number, we can just double check everything's plugged in right, because that's a big part of this course that'll always get you, is you might understand the theory, but number mistakes happen frequently. And so Al's done the math just about the same time I have, and he got 0.5365. That's also what I got. So our circuit switch time, oops, that's not what I wanted to do. There we go. Our circuit switch time ends up being, and I'll plug in the numbers here just so it's clear the math we did. So we have 4 hops times our propagation delay, which is 0.001, plus 3,000 divided by 9,600 plus 0.02, and that gives us our final number of C equals 0.5365 seconds. And again, we're doing it in seconds here. You could rewrite that as milliseconds or whatever you wanted to do on units. That doesn't matter as much, but you just keep it in seconds as it is. So again, with this problem, it's not so much the math that's the tricky part. It's making sure you understand. Oops. Hello, are we back? All right, I'm just going to give us, sorry about that, I jiggled a cord that shouldn't have been touched there, but hopefully we're back. Let me know when you guys can hear me again. Let me get off that screen because we're getting some feedback. Okay, yeah, all right, we're back. Great. Sorry about that. I like I said, I kicked the Ethernet a bit. But like I was saying, this problem isn't, the hardest part about this problem is getting where to start, which is what some of you guys were saying. You need to figure out, okay, I understand the basics of how circuit switching and packet switching work, but what does that actually mean for the calculation's sake? All right, so again, that's part one. We looked at the circuit switch time and we calculated that successfully. So now this is the hard one, is packet switching. Now, you probably have a basic understanding of how packet switching works, and if you read the chapter, you should have a little bit of a solid idea of the fundamentals of it and how it differs. But the main thing to remember is that in a packet switch network, we have a bunch of nodes, be they routers, hops, whatever you want to call them. But the idea is, instead of circuit switching, we don't establish one fixed path to take. Each packet is handled individually and routed individually. So if you have the home node here, the home computer, or the sending computer, I guess we could say, and the receiving computer, every packet you send may take a different path. So the first packet might go here, 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 then here. The second packet might go from here to here to here, to here, and then it goes the same way to here. 1, 2, 3, 1, 2. The important part basically to remember here is that each of the packets might go their own path, but they'll all travel 4 hops for the sake of this problem. So I've done 3 hops here, but whichever path the packet takes, it's ultimately going to take the same number of steps, but we don't know which way it's going to go. And so when we look at packet switching, the formula we use is a little bit more complicated than circuit switching, because the initial thing we have to worry about is the fact that we're actually using packets. If you look at circuit switching, we just took the whole message, so the length of the message divided by the bit rate. We just figured we were sending the message all in one big stream, no problem. But that's not the case for packet switching. We need to split our message into the packets that we're given. And so that's the first thing I guess we'll start with, is we need to figure out how many packets we actually need to send. So how would we go about finding out the number of packets we need to use for this problem? Because again, we can't just send the whole message because we're talking about packet switching. We need to use packets. How can we figure out how many packets are needed to send the message? Ryan says length divided by p, and if we look back at the variables again to just clarify what he's saying there, we have message length divided by packet size. Now you're almost there, Ryan. However, what do we have to keep in mind when we're talking about the size of our packets? Because it's given that packet size is 1080, but we also have to account for these header bits per packet, right? Every packet in datagram packet switching needs header information, so the routers know where to send it. But those header bits take up space in the packet that we can't use for data. So you're almost right, Ryan, but there's one additional calculation we have to throw in there, because each packet has to contain data packets and header. And so you're pretty much there if you change P into something else. And so you pretty much got it, so I'll just go ahead and cut out the waiting, because I know you can figure it out. I don't want to wait the 5 minutes or however long it feels. So basically, to find out number of packets, let's get back to black text. Number of packets equals message length, and you're absolutely right about that, divided by the packet size minus header, because every packet has to include the header bits, and that's space that we can't use for data. And so if we plug in the numbers to that calculation, we have number of packets equals 3,000 divided by, and we have 1080 minus 80, because our packet size is 1080 bits, our header takes up 80 bits of data, and so that gives us, based on those numbers, number of packets equals 3. Well, I guess I'll just write out a number, equals 3,000, to make my math super clear, divided by 1,000, number equals 3. And so we need to use 3 packets to transmit this data. And that's the first part of our calculation. So we know that we're going to be using datagram packet switching, we need to use 3 packets to send our data. Now, because each packet is treated independently, we have to consider the fact that they're going to be sent across the network independently. And so the total time it takes, basically we have 4 hops because of n. We're told that n number of hops, we're always going to use 4 hops to transmit the data. And so we need to find out the amount of time it takes each packet to clear each hop. So we have hop 1 plus hop 2 plus hop 3 plus hop 4. And then I guess at the beginning here we'll say datagram packet equals. And so we know our message has to clear 4 hops. And so we just need to figure out the time it takes for each of those hops, for the message to clear each of those hops, I guess is the important thing to say. So H1 is the amount of time it takes for the message to complete hop 1. H2 is the amount of time it takes for the message to complete hop 2, H3 and H4, etc. Now, the important thing to remember is that we have whatever our network topology is, we potentially have a lot of different routes, and each packet is going to take its own route. So that means that in hop 1, luckily, we know that all packets have to go through hop 1. Because if we imagine our network is laid out like this with all our hops, this is basically, you can think of hop 1 as your default gateway or the first router you hit. We know that every single packet we transmit has to go through this first hop because there's no other choice. Our computer is connected to a singular router. We know they have to go through that one. And so we know that hop 1 is going to be all 3 of our packets have to travel through that first hop. And so if we look at our hop 1, we'll just do the hop 1 calculation for now. We'll take it a step at a time. Keep forgetting to change my font back. H1 equals, and again, we have 3 packets are going through here, times the time it takes for 1 packet to transmit, but then we have to account that we still have our propagation delay, so that's going to be plus D. That's what we're looking at for this first hop, because we know all 3 packets have to go through there. There's no possibility that they could go anywhere else. They only have one choice. We know that the packets take T amount of time to send, and that's just like what we did for the message earlier. And then because they're going through a delay, one hop, they get delayed. And so when we plug in these numbers, again, how do we find the amount of time it takes to send one of our packets? Very similar to the message we did before. So remember, this time we're talking about how long it takes to send a packet, not how long it takes to send the full message, just how long it takes to send a packet. Let me give a hint here. So we're talking about 3 times, and we know the size of our packet. We calculated that earlier. And then we know how fast we can send data. So we have P divided by B this time instead of the previous L divided by B. Because we're only sending a packet, we're not having to send the full length of the message, plus D. Does that make sense? Okay, just looking at it now, Al's got it with P divided by... So Al says P divided by L, it's P divided by B, but you essentially had it there because it's packet size divided by the rate that we can send data. Because we know each packet is 1080 bits, and we know that we can send data at a rate of 9600 bits. And then we just have to do that 3 times because we're sending 3 packets. And then we add in the delay. And we don't have to add the delay in per packet because we are only concerned about the hop. So all 3 packets are going through this first hop, so we just have to add in that delay once. So let me just write out the numbers here. Now we have H1 equals 3 times 1080 divided by 9600 plus 0.001. And so that ends up 3 times 0.1125 plus 0.001. And that ends up being equal to H1 equals 0.3385 seconds. So that's the amount of time it takes for our message to clear hop 1. And again, hop 1's a little bit special because we know all 3 packets have to go through that hop, the same hop, because they have no other choice. And that's why we do the 3 times and then our calculation. Because we're basically we're transmitting 3 packets over that 1 hop. But I think I've made a strong emphasis saying that's a special case. And so now we're looking at hop 2, which is different. Because once we clear this first hop, we don't know that we can't guarantee that all 3 packets are going to go through the same hop. And so if we can't guarantee that all 3 packets are going to go through the same hop, which one packet do we care about? There's one particular, if we're trying to find the time that it takes the message to get across the hop, which of the individual packets do we care about? Again, we're trying to find the amount of time it takes. So if we have to pick one packet out of the 3 that we're sending, which one do we care about? Because remember, even if we don't know the route they take, we know they all have to take 4 hops. And Al says last packet, and that's absolutely right, because the last packet is going to take the longest, right? And that's going to set how long it takes the message to go across. Because whatever packet takes the longest, that's the time that it's going to take the message to go across, because the full message isn't complete until all the packets make it. And so for this problem, we know all the packets take the same amount of time. And so we don't have to, all we have to really worry about is we do the calculation we did for H1. So we have H2 equals, but we only have to do it once because we're only caring about the last packet to cross. And so that also equals H3 equals H4. Because for all of the last hops, again, we can't guarantee that all the packets are going to go through the same route. As far as we know, right? H4, it's likely that we might have the same situation where they might all go through it, but we don't know that. We can't guarantee that. Because that might differ based on how we're sending the message or who we're sending it to. All we can guarantee is that we know that they'll all go through that first hop. And so for H2, H3, H4, H2, H3, H4, our math is simply basically what we did before, 1080 divided by 9600 plus 0.001, which gives us our time of 0.1135. And so now we know, oops, I guess. So now that we know H1, H2, H3, H4, we can just add them all up. So for our datagram packet switching, we have 0.3385 plus 0.1135 plus 0.1135, oops, that's getting messy, plus 0.1135. For a total time, and I'll have to plug in the calculator here, and that gives me a total time of 0. And I'll let somebody else calculate it just so I can verify our answers. Sorry, let me, there, now you can see the numbers again if you want to verify. Al says 0.679, and that is also what I got. So we'll do 0.679 seconds. And again, you can write that however you want. You could do milliseconds if you'd want to, but it's easier just to leave it in seconds, and that's fine. You shouldn't ever get marked wrong if you have different I guess prefixes, different scales. So milli should get you the same answer. So that's the hardest one, is understanding why we have to do that calculation in that way. Basically, it's because we handle each packet independently, and so the first hop, we know that all 3 packets have to go through it, or however many packets we have, all have to go through that first hop, but then we have to treat each packet independently after that point. So we just have to take the time it takes for the last packet to clear the hop. So that's why I said at the beginning, we're basically looking at the time it takes for the message to clear hop 1, for the message to clear hop 2, hop 3, and hop 4. We don't want to look at it at the packet level, because that makes you think you have to calculate all 3 packets in every time, but you don't. You're just looking for the amount of time it takes for the message to clear the hop. So we only look at the singular last packet, because that's going to take the longest to clear that particular hop. Al says, yeah, this class is nuts, and it's certainly different, and it forces you to look at things that you haven't necessarily looked at, or the way you've looked at things before. Okay, so again, that's part 2. We've done circuit switching, we've done our datagram packet switching, and now we have virtual circuit packet switching, which is great, which is easy now that we've done the previous 2. Because remember that virtual circuit packet switching is just a combination of datagram packet switching and virtual and circuit packet switching. So let me clear out circuit switching since we're done with that. Delete everything there. So virtual circuit packet switching is essentially packet switching, but there's a pre-established path. So it really is just a combination of the 2 previous methods we did. And so if it's a combination of 2, if it's datagram packet switching, does anybody have a guess of what the formula is going to look like? So we have virtual packet switching, or virtual circuit, equals, and again, it's datagram packet switching, but with a setup path. So does anybody have a guess on what formula we're going to use? It really is just a combination of the 2. And so Al's pretty much got it. He says we have, because it's a combination of the 2, we have to set up our circuit that we're going to use. Then we have to do our datagram time, because we're going to datagram packet switch over that circuit we just did. And then plus our teardown. And so, again, we're given S and T in the original variables, just like circuit switching. So we have 0.2 plus datagram plus 0.02. And then we already just, in the previous step, we just solved for datagram. So we have VC equals, or virtual circuit time, equals 0.2 plus 0.6790 plus 0.02. And so that math is pretty simple. And we end up with a time of 0.8990 seconds. And that's pretty much it. That's it for the virtual circuit, because it really is just a combination of the 2 that we did previously. And that's why I suggest doing it in this order, not in the order the book gives you, because otherwise you have to jump ahead and do the datagram as part of virtual circuit, and it gets more confusing than it needs to be. But that wraps it up for the math of that problem, because we've calculated circuit switching time, which is just setup plus message transmission plus teardown. We did datagram, which is the time it takes for the message to clear each hop. And then virtual circuit, which is just setup, datagram time that we just calculated, and teardown time. And so that should give you everything you need for that problem. And that's, yeah, I wanted, that's the main reason I knew this session this week would be a little bit busier, is because that's a tough problem to get that first step on. Even if you're familiar with packet switching, you don't necessarily make the connection with the packets and the times they take. But yeah, it's a bit of a bugbear of a question, so we might run this session a little bit longer today, just in case, just to get a few more questions rather than just this one. But now that we've covered that one, is that clear to everybody, / does anybody else have any other questions? I'm sure there's at least a couple more we can do in the time we have. Let me clear out the canvas so we can start fresh. Ryan says that makes more sense now. Yeah, it really is just getting that first. Everything makes sense when you walk through it. You just need to basically know where you have to start. Because reading through the book will give you an idea of, okay, circuit switching makes sense. I understand that circuit has to be set up, the message happens, then then you tear down. But actually putting the numbers in there makes you have to think about it in a different way. And packet switching. Packet switching is the one that's tricky. Because I know when I did it the first time, I didn't realize that first hop was unique. I didn't think to say, oh, wait, all 3 of the packets have to go through that first hop. I think I handled each of the hops independently, so. And again, just remember that there will be another session on Sunday from 10 to 11. It is fairly early, but so if you have any other questions that you don't think of now, or you keep working through and you hit another one, Sunday is available. Al, we can address your question. Michael, just logging in, will it be posted later? Yeah, as soon as, since it's a live stream, Google or YouTube takes a couple hours to process it and post it, but it will be available on my channel for you to watch later. Yeah, okay, so yeah, it looks like we have some activity questions. So let me pull up the activity and we can take a look at it. But I'll make a post in the discussion board with the link as soon as I see it's done. But if you're paying attention to the channel, you might catch it before I do. So let me see. So Ryan, the solution video will be posted tomorrow after midnight tonight, when that solution video will be posted for you to review it. But we can take a look at it now for sure too. Let me take a look at the problem set. The video is it's going to be posted late because the idea was to have you guys attempt it first and then review the video if you were stuck. But let me pull up the activity right now and we'll take a look at it and see if we can address something now. Okay. All right, so which part of the activity do we want to look at here? right, let's see. Okay, so if we're looking for received carrier power in dBm, let me make sure I have everything here. It's probably just, Chris is saying he's stuck as well. I think there's something simple. I think it's probably just terminology. I know a lot of people have issues with terminology on this type of problem. So we have, let's see. Okay, so for question 1, for the received carrier power, we're given that P sub r, which is received power, equals 10 to the, there's going to be no easy way to do this in Paint, but 10 to the negative 11 watts. And so the question is asking you to take that number and convert it to dBm. And so the first step generally is we need to convert this to decibel in the first place, right? And so, Al, why don't you try posting your formula? We'll see if you perhaps overthought this, but basically we need to take this number and convert it to dB. And so how do we do that? What's our conversion from decimal to dB? So Al's got PR equals 10 to the negative 11 equals 10 log 10 to the negative 11. So that's where he's doing the conversion to dB. So we have PR in dB, PR in dB equals 10 log 10 to the negative 11. And that ends up, let me do quick math here, 10 log 10 to the negative 11 gives us, where are we, equals negative 110 dBW. Now again, that's got us into decibel, but we're still in watts. And then at that point, like Al said, in order to go from watts, dBW to dBm, we have to add in 30 dB of difference. So now to get that, P R D B M equals negative 10, 110 dBW plus 30. And so that gives us PR in dBm equals negative 80 dBm. I guess that's one extra dBm, but that's what we're looking at there. So Al, it looks like you had it as you needed it there. And I'm actually going to bump the study session by half an hour, so we'll have another half hour just to address some of this activity, if we need it. If we finish up sooner than that, that's fine too. But I forgot how long it takes to walk through that packet switching problem. So that's what we're looking at for, I guess we might mark question 1 there. So that's all we really need to do there. We don't need to worry about too much of anything else. It's just checking your conversions from the watts from a decimal to a decibel value, and then making sure you can get from dBW to dBm as well. Can you go over how you completed the 10 to the negative 11? So I assume you're talking about Okay, so yeah, 10 to the negative 11 is the power, the received power in watts. That's given to us in the initial numbers. So at the top of the practice problem, it says use following information, and then one of the numbers it gives is P sub R equals 10 to the negative 11 watts. And again, this is how I have to do exponents here. It's not great. But that's the given received power in watts. So P sub R stands for received power, and that power level is 10 to the negative 11 watts. And then we do the 10 log because we need to convert from decimal to decibel, and so we convert our watts into dBWs by doing 10 log. And then we need to go from dBWs to dBm, so we add 30 back in. But this original number is given to us in the problem specification. Question 5 for the activity. Sure, we'll jump ahead there. Let's see what we have for question 5. So for question 5, what is the carrier to noise ratio at the input to the amplifier? Okay. So this assumes that you've calculated question 2. Okay, Chris, why don't you post what you're trying to do? Because I'm not 100% sure what you mean by expanding the parentheses. And then I'll address Michael's question really quick while you're giving me a little bit more info on that. But yeah, so Michael, the negative 110 is just, we're converting, we have to do our 10 log, which is our decibel, or our decimal to decibel conversion. We always do 10 log decimal to get that number represented in decibel. And then to reverse that process, we do 10 to the power of decibel divided by 10. Let me write this out. So 10 log decimal equals decibel. And then 10 to the decibel divided by 10 equals decimal. Oops. And so while Chris is thinking about his for 5 is basically, it's asking you for the carrier to noise ratio at the input to the amplifier. So we know, it's assumed that you've done 2 correctly, because 2 you had to calculate the received noise power at the input. And we need, because we're trying to find carrier to noise, we need to know the carrier power and we need to know the noise power. Those are the 2 numbers we need to find the carrier to noise ratio. And so let's go for 5. Assuming you've done 5 correctly, what you're looking at, all you really have to do is you have your signal level, signal to noise equals, and I guess we'll do in decimal, we know it's going to be equal to signal divided by noise. But in decibel equals signal minus noise. Because remember that decibel subtraction is the same as decimal division. And so that's why I'm not 100% sure. Okay, let me see. 10 log negative 115. So Chris, that is correct for problem 2. So you calculated the noise out. And so that's giving you the received signal noise power. So that's basically, you've done question 2 there. And that looks fine to me. That looks like you did it correctly. And so if anybody's wondering how to do 2, that's pretty much what you're looking at there. You have 10 log KTB. And so his numbers there, you have 1.38 times 10 to the negative 23rd, which is K. That's Boltzmann's constant, the decimal representation of Boltzmann's constant, times 296, which is the temperature, 273. Okay, so yeah, it looks like we have some agreement that we're on the same page for 2. And so for 5, now that we've calculated, for part 1, we calculated the received power, the signal power. And then Chris has just showed us for part 2, he's calculated out the noise power. And so all we have to do for 5 is, because we know these 2 decibel numbers, we're going to use the decibel signal to noise formula. And so we just have negative 80 dBm minus our noise level, which is negative 115.13 or 1, whatever you want to say, dB, or 1.5. I can't. Let me double check your numbers. 1.3 dBm, which gives us a ratio. Oops, shouldn't have clicked down. Equals 35.1 dB. So I think you were just overthinking it a little bit. I think you were doing more math than you had to do for that one. Because we're just trying to find the ratio of how much signal per noise. And again, in decimal, we know that it's signal to noise. To find the ratio, we divide out. And in decibel, subtraction is the same thing as decimal division. So we just have to subtract our 2 numbers instead of dividing them. And that'll give us just dB, because again, dB is how we express ratios. There's no power involved there. It's just a ratio, so it's just dB. But that tells us what our signal to noise ratio is. It's 35 dB signal to noise, or carrier to noise, whatever you want to call it, same thing. So I think you were just over mathing yourself on that one. I thought you couldn't add 2 power units. You're right, Al, you can't, but we're subtracting. And I know what you're thinking. You're thinking that there's a double negative here, but we can't think about it that way because that doesn't work the way we want it to. We're subtracting a negative, which looks like Michael says, I'm lost. Did you divide the numbers? We subtracted the numbers. Yeah, and it's tricky. All that matters is the fact that this is a negative sign and not an addition. It technically works out to be equivalent to adding, but we're not adding, we're subtracting a negative. And that doesn't normally matter in decimal numbers, but it very much matters in decibel numbers. Because you're right, we can't add 2 power units. But by subtracting a negative, we're getting this. The answer involves addition, but we're not actually adding 2 decibels together. And I can break that down and show you why it works. But Michael, so we're subtracting the 2 decimal numbers there, because the decibel numbers, and I'll show you why that works. Just I want to make sure Michael's clear on why we subtracted the numbers here, because signal to noise for decimal is how much signal there is per noise. So that's division. That generally makes sense in decimal numbers. But for decibel, because we're working in decibel, subtracting decibel numbers is the same as dividing decimal. And I'm going to have to break that down to explain to Al why this works. And this is a tricky one. So we subtract the two numbers here, and we're subtracting a negative, so we can technically add. Other way around, Michael, because we have negative 80 minus negative 115.13. And order matters because it's subtraction. So we have signal minus our noise. So negative 80 minus negative 115.13 gives us 35.1. And I can show, and I want to show Al why it matters, why we can do a double negative and technically add it. So I'll start that right now, but let me know if that's still not clear and I'll go back. So here's why we can do the technical double subtraction. So let's say we have 30 dBW plus 40 dBW, right? And this is what you cannot do. You can't add 2 power units, because let's convert these to decimal now, because this looks like you should just be able to do equals, well, that equals 70 dBW, doesn't it? And the answer is no, it does not. And so I'll put does not equals, you cannot do that, because if we convert these numbers to decimal instead, so we do 10 to the 3, I guess I'll just write out 30 divided by 10, times, because remember, decimal addition is the same, decibel addition is the same as decimal multiplication, times 10 to the 40 divided by 10, and that equals, I could probably do this in my head, but I want to make sure I'm right. So 100, and what units do we have here? We have watts times 10 to the 4 divided by 10, which is 1,000 watts. Oops, 1,000 watts equals 312 watts squared, square watts. Which, for our purposes, doesn't make any sense. We don't deal with square watts. We can't do that. But, so that's why we can't add 2 power units, which, Al, you're absolutely correct. We can't add 2 power units. But now, let's look at this situation. So we have 100 dBW minus negative 50 dBW. And this does, in fact, equal 150 dB. Now, why? So let's take a look. So here we have, we'll convert it all to decimal again. So we have 10 to the 100 divided by 10. And remember, decibel subtraction is the same as decimal division. So we have 10 to the negative 50 divided by 10. And so now if we crunch the numbers on this, 10 to 100, oops, 10 to the 100 divided by 10 gives us 1 times 10 to the, right there, divided by 10 to the negative 50 divided by 10, which is 1 times 10 to the negative 5th. So that's what we're looking at in decimal, and if we divide those numbers out, oops, I keep mistyping into my calculator, divided by 1 times 10 to the negative 5th. That gives us 1 times 10 to the 15th. And if we convert that back to decibel, so 10 log 1 e to the 15th equals 150 dB. And so that's the very important distinction that you have to make, is that subtracting a negative in dB is not the same as adding, even though that's what we've been trained to think because we've been working in decimal for so long. That is actually not at all what's happening. Because you're dividing, you're technically dividing instead of doing just the multiplication. So you'll notice that since we have the negative here, since we're subtracting by the negative, we end up dividing by, basically dividing by a fraction, right? Because 1 times e to the negative 5th yeah, and so I hopefully that's clear, but that is a very important distinction to make. This looks like something that you can't do, but you absolutely can, because this is what matters right here. The initial subtraction is all that matters. We're actually subtracting a negative. We're not adding anything. As far as the math works out, it's equivalent to adding, but it's legal to do as opposed to actually doing the addition. So, yes, that is a tricky one to get, and I can see why that would confuse you and make you overthink something. But you're absolutely right that we cannot add power units, because then we end up with this situation where we get squared units, and we don't want to deal with that. It doesn't make sense for the way we're working with them. Alright, and again, the solution video and the answer key to this practice problem set will be available after midnight tonight. So tomorrow, before you have to turn it in, it'll be available for you to go through and make sure you've done everything correctly and double check everything. But because it was requested, I wanted to go through some of them tonight. But it will be available tomorrow before the due date. So you can go over, this is intended to just be practice problems for your own benefit. But make sure you do get them and turned in, because you're being graded for making sure you practiced. So absolutely worth doing. But is there anything else anybody else wants to talk about? Because we have 15 more minutes. We can keep talking about the activity, but again, that'll be available this evening. So if there's anything else we want to go over, there is another study session Sunday morning, 10 to 11. So if you work on the homework between now and then, hit something that you're stuck on, show up then, and we can do this again. I probably won't be able to extend that one out too long. So if you want to come prepared with questions and be ready to go, that would be great, because I'm going to be busy pretty soon after that one. And then again, for whoever jumped in late, this video will be available as soon as YouTube makes it available. That's a little bit beyond me, but it should be by this evening. It only takes a couple hours usually. Yeah, no problem. I think these are useful. I did them last semester and they were useful there, and I think they're good to have, and it gives you a little bit more of a way to directly ask the questions you have, because I know Dr. Helm's sessions are good, but they are kind of more just reiterating the lecture material and going over the lecture material, but this hopefully gives you and again, feel free to email me if you have a specific question that you don't want to bring up in a study session, or something comes up right after now that you forget about, whatever. Email me. As far as you can email me through Blackboard. I think Dr. Helm posted my contact information. I assume that's correct. Let me double check that that's right. That should be one of the first announcements he made. but I will try to get back to you within 24 hours on email. So please don't email me Sunday afternoon to get something done for that night for the homework, because I probably will not get back to you. I tend to be very busy on the weekends. But I will try to get back to you within 24 hours if you email me. Sundays, weekends are hard, but other times I will get back to you as soon as I can on those. All right, I think we're good here. So thank you everyone for attending. Hopefully it was useful for you. I'm going to end it now, but again, contact me individually if you have more questions. The activity stuff will be posted tonight by midnight, so you can look at the solutions and double check your work in addition to what we went over now. Come back on Sunday, 10 to 11, for another one of these study sessions. All right, have a good day, everyone. Bye.